Okay, so happy Monday. Welcome back to probability and stochastic processes. Today, what we're supposed to talk today. So let's see what we talked last week. We started talking about random processes. We said we are moving one dimension higher. We bring time involved instead of having random variables and set of random variables, random vectors. We have the set of random vectors changing in time that make a process, and that process is called random process. We said, okay, the easiest random process can come from the Bernoulli process, that in Bernoulli you just have success and failure and probability of success and failure, and this is just trials happening, many trials, like you are flipping a coin 100 times. For each trial is success or failure, and that start with Bernoulli, amazing Swiss mathematician, Switzerland. Yes, so he actually modeled this system, and that called Bernoulli process. But we changed the Bernoulli process, not me, of course, not me, but other mathematician and great scientists like Poisson, French mathematician, Poisson, that said, okay, if the Bernoulli happening in a discrete times, when we bring this time slice smaller and smaller and smaller, we might get something nicer, like a continuous version of Bernoulli, and he did that. But today we're going to talk about Poisson more. Last class we didn't cover it nicely. So we're going to talk about Poisson and focusing on homogeneous Poisson, make it more restricted in actually lambda. In lambda and timing, we're going to make it more restricted. That's called homogeneous Poisson. And what else we're going to talk? And also we want to talk about time for waiting time. Waiting time for success or events happen, waiting time. So the waiting time bringing up another distribution that is exponential distribution. Exponential distribution is all exponential distribution, binomial distribution, geometric distributions, Poisson distribution. They are all variation of Bernoulli. That's why I'm saying the Bernoulli one was the main, like a stepping stone for all of these new distributions that coming after that. So we're going to see how from Bernoulli we can get them. And we also might talk about the stationary a little bit, how we call a system stationary when the change of the system is not very related to past. It's like a memoryless. You don't keep the memory, you just, the probability of something happen from now is not depends even now. It depends the time that you're gonna do that process, for example. That kind of systems called memoryless. Later on in this class, maybe next class, I start about Markov processes that they have memory. Markov processes, but they don't have very long. They have very short memory. They just remember the past, not so many times past, A very simple case of memory systems. a Markov process. I think Markov was Russian. I'm not sure. Need to check. So, but today we want to talk about memoryless systems. But it still works. This is the stepping stone for all of these distributions. Okay, let's get started. Let's go back, recall Bernoulli process, the Bernoulli trial. In that time, we call that trial because it's still not time involved. It didn't, but the trial is actually time, kind of time. So we call that Bernoulli trial. We had delta t that, so we are doing the trials in this delta t time, and this delta t time, if it's getting smaller and smaller, make the Bernoulli trial that is actually a discrete random process to a continuous random process. So how this is happening is actually coming from the binomial part of that. If you remember the binomial, I didn't remember too, I just went and found it out. So it's like that. This is the coming from binomial. In binomial, we are counting the number of success. Binomial is one of the variation of Bernoulli. In binomial, you are counting the number of success, like probability of having, for example, 2 success after trying 10 times, for example. If the k is small k and you are trying n times, it's coming from selecting k from n. Probability p is the probability of success k, and 1 minus p, n minus k. If you remember this, this was binomial distribution. That is a variation of Bernoulli. So if we change this a little bit, I mean do these limits, it means if we, in this function, we expand it and make the delta t smaller and smaller, and at the same time p is smaller. Why we do p? Because we want to have the rate constant. We don't want to change the rate. The rate of success is the probability of success in delta t. The rate of the success we want to stay still constant when we are decreasing the time. That's why we do at the same time p and delta t together. If we do that limit in this binomial, we're going to get new distribution. And that distribution called Poisson. Where I clean this up. So the Poisson distribution is a continuous form of binomial distribution, kind of. And because binomial was a variation of Bernoulli, that's why we consider Poisson is a continuous form of Bernoulli. But in reality, is coming from binomial. Okay, that's so this exponential family is coming up after expanding. When expanding the series add up to exponential. I'm not gonna prove it, but if you are so interested, you can go find it out. But that's the reason that we have exponential families here. And exponential families are amazing. They are really amazing. Anytime you have probability of exponential, you need to be happy. Because with that simple tricks, you can bring down that exponential with just getting some log and minus log, make a max to mean, and easily change it to linear. Because why linear? Because e gonna go and just exponent gonna stay out. We did that before. Remember when we were counting, when we were computing probability of conditional probabilities for Kalman filter? We did the same. Okay, so That is the history behind Bernoulli and Poisson, the French mathematician and the German one. So normally is a continuous time of Bernoulli. Okay, let's go deeper in Poisson distribution. So normally Poisson distribution counts the number of random events. Anytime you are dealing with numbers in random events, you're going to see Poisson. Like, for example, I told last week that when you are dealing with a false alarm in a radar is mostly Poisson distribution because the number in a time is normally considered constant. So it's random, but we are dealing with the number. And that number is coming from Poisson distribution in a certain time. So in Poisson, you have one lambda all the time. You have lambda, and you have t. This t is like duration time. Is a time that we are doing. For example, when you do a scanning, radar is working like that. Scanning happening in, like, for example, 10. I don't know. I don't know exactly, but maybe millisecond, at least 1 millisecond, for example. Each millisecond, however, it's much higher, probably new radars, but that time is a scanning time. That time is important for this this Poisson random process. So this probability of having, for example, M detection in this period coming from Poisson distribution. So what we want to count, we want to see, okay, what is the probability of having 10 false alarm if the lambda is 0.01 and the period is 1 millisecond. We can compute that. Based on what? Based off Poisson distribution. We're going to see examples soon. Okay, so this is how Poisson works. But there is some conditions, of course. The conditions that you have here, actually, they are big conditions. Independency. We are saying, okay, this trial and the other trial, they are independent. They're not dependent on each other. Like the number of detection in this period that radar detecting is not related to the other. If they are overlapping, yes, but this time not overlapping, they are independent. Events occur independently. Another point is this lambda things. This rating of actually detection or rating event rates is mostly considered constant. However, we have different type of Poisson. Sometimes lambda is a function of time, but if it's constant, we call that kind of Poisson homogeneous Poisson. So whatever we are talking today and later, probably, because we're not going to learn too much about Poisson. We have other things to be worried about. We're just going to consider the simple case of Poisson that's called homogeneous Poisson. And in homogeneous Poisson, this omega is a constant number. It's just a constant number. It's not a function of time. It's a constant number. So that's why I brought this here up. So we have two conditions, independency and constant. However, for homogeneous, we have more constraints to make it much easier even. Okay, so that's a Poisson random process. So the mean for random process, okay, if we imagine we have a period time, for example, this period t, and t plus small t plus capital T. This capital T is important, not T. That's why this system is kind of memoryless. We don't care about past. And this lowercase t is not important. This capital T is important. So the number of events that happening here, is depend on two things, this and lambda, not a small t. Okay, so if the rate of success is lambda, expected value of this number is just lambda t. Because the t is multiple delta t's, so we just multiply that by lambda, and that's going to be mean. So the mean of Poisson random process coming from this. However, it has lots of computation. You can compute that. I'm not, because it's so hard to do all these integrals and series and those things. And this is, you are not math students, you know. And you have always computer to do those kind of maths for you. But the idea is coming from that. The rate is lambda, so in a period t, so this gonna give you the mean. Mean of Poisson random process is lambda t. What about, okay, so let's clean this up. So what is the interpretation? So interpretation is that on average, lambda event occur per unit time. So as I mentioned, so in t period, you're going to have, you expect this much events, because the expected value, the mean, is coming from that. And what about the variance? This is, I don't know, the only random process or random variable that covariance or variance, and I'm not sure, but this is one of the good property of Poisson random vector, a random process, that expected value and the variance are the same. And why? Again, it has lots of formula to prove it, but in a very general, just speaking way, we can say the reason is because in this system, we just have two things, lambda and t. And all of the uncertainty coming from these two. And you just need to multiply them together. So this is the only uncertainty we have. Why? Because we said it's independent. This trial and the other independent. There is no another t. There's just two constant. T, t is not constant, but is in the period t, and the lambda is constant too. So the variance is just this. So the variance and mean are equal. No, it's possible to prove it, of course, because we have E and we have the formula for variance. We can write it up and put the formula and make the integral and find it up, of course, but you're going to get the same result. But in general, like generally speaking, is just the reason is because the only uncertainty coming from that. let's look at this. If we draw the Poisson distribution, for example, this is T. This is T. And Poisson distribution is something similar to normal distribution. This is probability of m is equal to m. So this is similar to normal distribution. If we increase this lambda t, if we increase this lambda t, this is actually going to be exactly normal distribution eventually. This gives us something new coming to, we can explain that in the next slide. That's a coming central limit theorem. It's an amazing theorem. We're going to see that. I actually draw this in, so this is for example, lambda 4, and m is, for example, lambda t is smaller. Then make lambda t bigger, it's going to be exactly like that. And this is kind of normal distribution. And this gave, when I saw that, I said, oh my God, here is a time to talk about this central limit theorem. That central limit theorem is a very basic cornerstone in probabilistic, and for sure in robotics, in computer, and AI, they use it. So is the stepping, cornerstone actually is not stepping. Anyway, it's a stone. It's another stone that we need to, based off that, do lots of things. And that's the power of repeating things. When you repeat things a lot and add them up and then get average, you're going to get normal distribution. That's why when you go to the, for example, ocean and collect sands and put them together, after a lot of sand, it's going to get a very nice bell shape. And so many other things. That's why we see normal distribution a lot in nature. Because it's repeating things. When you are repeating things a lot and a lot and a lot, distribution trend to normal distribution. And this is the basic of so many things. Later we can see that. That's called central limit theorem. I said, okay, is it time to explain that? I'm still in the middle of Poisson, and we're going to come back to Poisson. When I saw that diagram, I said, okay, I forgot to talk about it. Let's do it now. So central limit theorem is that when we sum or average a large number of two things, independent and identically distributed. Identically distributed means they all have the same distribution. That we had it in the previous example. So like those sands, they all have the same almost weight. And they have same distribution. When you put them together, add them together, the shape becomes bell. So that's called central limit theorem. So probably in the papers or other things you saw that before, and but here you see how we can. And it's easy to prove, it's not difficult. So because we just need to add those random variables together. Like in this example, you can see you just need to add them together. However, you need some normalization factor. and actually subtracted with the number of n is the numbers, and the mean subtracted with this and of course do limit when n going to infinity, and you're going to get a normal distribution. That subtraction is because to get this 0 as a mean. That's it. So it's possible to prove it, but you need to go for infinity. So an infinity not exist. But we don't care. If we go enough, make it big enough, it's almost okay. Approximately okay. Or probabilistically speaking, okay. So that's the central limit theorem, one of the amazing theorem in probability. And intuitive meaning is that as we combine many small random effects, their total behave like a Gaussian. That's amazing intuition. Okay, so that was central limit theorem. Sorry for interruption. Let's go back to Poisson distribution. Poisson still is good to cover because it has something else that I'm gonna talk about, and that's another distribution called exponential distribution that give us the timing interval, waiting time. So many applications for waiting time. So how you can model waiting time with this, with the exponential family that coming from Poisson. But not normal Poisson. Let's make Poisson more restricted. Homogeneous Poisson. Homogeneous Poisson is a type of Poisson that it has constant rate, of course, but the expected number of events per unit is constant. The expected number of events per unit is constant. It means this delta t is constant. Also, this independent, we knew that before, independent increments. The number of events in disjoint time intervals are independent. If you have two timing, the number of events that happening in each one, independent of each other. Okay? Another one is stationary. But stationary, I told you what that means. Stationary means the place that we are is not related to the probability of something that happened later. So the probability of seeing a certain number of events depends only on the length of that time interval, not the position that we are now. So in formulation speaking, like mathematical speaking, we can talk about T and capital T. So if the number of events in time T and T plus capital T is not M, for example, this is exactly similar. This is similar to probability of N T. It's not dependent on the small t. As you can see in this formula, there is no lowercase t. It's eliminated. So lowercase t means the position right now. It's not that this probability of events later is just depend how much this interval time from now is, you know. It's not related to where I am right now or what time I'm waiting right now. Okay, so That's give us the idea of memoryless that we're gonna see that soon. Doesn't have memory. Even not short memory, you know. And it only depends on interval length, not t, okay? Another thing is no simultaneous events. And this simultaneous events is something that we see that a lot, you know. So this simultaneous events is just a mathematical ideology. What that means, it means like ideologically two events that happen at the same time have a very low probability. The probability of happening at the same time is very low, close to zero. So the probability that two or more events occur at exactly the same time is, probabilistically speaking or mathematically, ideologically speaking, is zero. Okay, if you have these properties, that Poisson is homogeneous. Okay, why we want this? Because we want to find something else that is waiting time. So if the system is homogeneous Poisson, then we can find waiting time between events. Ooh, wow, between events we can say how much we wait to get, for example, first target, the radar, for example. So, or probability of after 1 minute I get probability of getting target when I stay 1 minute is how much? How much is that probability? So this is coming from something that is called waiting time. Okay, so maybe you ask me, what is this coming from? It's not, this relationship between this and Poisson. I'm gonna tell you. A long time ago, once upon a time, when I was talking about Bernoulli, I said two things. I said variation of Bernoulli is not just binomial, but is also geometry. Geometry distribution. Geometry's distribution is look like summing or like something like that. It's like exponential curve. We had that last class, if you remember. And a geometry in a Bernoulli was actually telling us number of trials. This is important, you know. Number of trial until the first success. Do you remember that? I didn't. Just take a look at that slide to remember. But that's the basic of that. So this geometry distribution, the formula was something like that. P of M is 1 minus P. P is the probability of success, of course. M minus 1P. Okay? So you know what I want to say now. Okay, what about we go again delta t going to 0 and p going to 0. We limit that. Limit p of m is equal to m. So we're going to get this. So this formula, after expanding the numbers and add them up, is going to bring that exponential family out. Because series and exponential families are very friend. Most of the series is going to sum up, not most of, many of them, to the exponential family. That's why exponentials are so amazing. Okay, so that was good. So we have right now another distribution, and this distribution called exponential distribution. And what this exponential distribution is saying, still we have lambda, still we have t, but this exponential family telling us probability of waiting t time to get first success or first events, whatever. Like in radar, probability of waiting 1 minute to get one detection, for example, to get first detection, something like that, if we want to practically explain it. We're going to see examples soon if we get a chance, okay? So let's clean this up. So interpretation describe how long you wait until the next event happens. And this is memoryless. What that means, it means, for example, you're going to see the example, very good example of that is in battery failure. In battery failure, this happened a lot. So in battery failure, you have some capital T. So for example, say, okay, capital T for battery is 1,000 hours, for example. After 1,000 hours, it might get failure. And but if that follow exponential family distribution, you need to count that from any minutes that you are starting. You know what I'm saying? If you already used it, for example, 100 hours, so that 100 hours, you're going to start it fresh from the time that period. That period need to be 1,000 hours, for example. That period need to be 1,000 hours, not past. So this is showing like a memory less property of waiting time. It's not fair, I know. So meaning the property of waiting an additional time t for the next event doesn't depend on how long you are already been waiting. What they call it, decay time? We don't have decay time in this. Maybe, yes, maybe it's not that realistic, but it still works for some systems, okay? But that's why we make the system so restricted and limited, you know, that homogeneous conditions is not always true. Okay, in this case, waiting, if the waiting time following this exponential family, exponential distribution, the expected value of waiting time or the average waiting time is just 1 over lambda. It can be computed easily. You can try it. Just you need to get integral. It's not difficult. I think this one I did that, but I don't have time to do all part of that. But you just need to find, because E of t, this is not that difficult. The integral from 0 to infinity, t f of t, d of t, and if you put that in formula, you're going to get something like this, 0 to infinity, and it's going to be 1 over lambda. Yeah. Also for covariance, you can do that. For covariance, it's going to be a little different. We can see that next slide. I don't need to write it up here. Okay, so because, oh, okay, that's a diagram. That's a diagram. That diagram that you can see is exponential. Power exponential if the exponent is negative. So normally, exponential is like that, e of x, but this is e of minus x. Don't forget. E of the exponent is negative. Okay, so let's go for mean and variance. So the mean is like that, it's just integral. The variance is also integral because this part is complicated. If you compute this part, you're going to get 2 over lambda 2, and this is 1 over lambda 2, and the overall going to be 1 over lambda 2. It still is nice. It still is very close form and nice. So the variance of exponential family. We're going to see exponential family also in robotics a lot. Application of that is a lot. Example, radar object detection. So we went through this example last class. That's why I'm not going to go too much. So we know probability of success and delta t. So because they are very little, we can consider it Poisson. Other than that, it's Bernoulli. Because it's Poisson, so the lambda is 2 detection per second. It's just radar object detection. It's nothing complicated. So it means in each second, you just can you detect 2 detection. So you can find the probability of, for example, M detection in t time. That's follow this distribution, and the mean. Oh, that's a time. Time between these detections. Average time between these detections follow exponential family distribution 1 over lambda. That is half a second. Another example is waiting time between ultrasonic sensing. Imagine your robot using ultrasonic. Ultrasonic is just sending sound and listen and computing the time to get distance between targets. So anyway, a mobile use ultrasonic to detect nearby obstacles when it's navigating in a hallway. The sensor emits sounds. Okay, what will I explain? So let's see what is the timing. Oh, shouldn't show that at the beginning. Okay, the given parts, each detection happen every 2 milliseconds. Okay, each detection attempts. We send like that radar that sending signals. Here also we send every 2 milliseconds, we send a signal. We send a signal and waiting that noise, that sounds to come back to compute the distance, whatever. And probability of detection is very little too. Probability of detection is 0, 0, 1. We have these 2 values. We need them to find lambda. Lambda is half per second. So it means in 2 seconds, we can detect 1 object. Probabilistically speaking, of course. So on average, the sensor detects 1 new obstacles every 2 seconds. So the waiting time following the exponential distribution, lambda given, t not given, but we can do it for different t. Like for example, if let's see, if for example t is 2, if t is 2, so E of t gonna be 1 over, oh, this is, sorry, if it's 2, the probability of weighting, we can find the probability of weighting. We just need to put 2 in this function, and we have lambda, so we can find the probability. Another example to do it fast is memoryless property. The memoryless property is the example of the battery that I mentioned. Imagine failure per hour is 0001. It means 1,000 hours. You need to wait for failure, but start from the time that we are starting. If the system was off when we started right now, we count it from now. Now suppose the robot has already opening 700 hours before, but we start working right now. So question is, what's the probability that the battery lasts another 300 hours? So that's not related to past. So we just can put that in a formula, fresh instead of capital T, and get the new value. So interpretation, the probability depends only on the additional time, not past. Okay, that was my presentation today. Don't forget to look at this debate link. We're going to give you lots of amazing ideas about Poisson distribution. Any other questions? Okay, so see you Wednesday.